Wieso ist denn das jetzt losgegangen?
So.
So, jetzt müsst ihr meinen Bildschirm sehen.
Okay.
Oder?
Ja.
Ich sehe deinen Bildschirm. Wer
Ja.
fängt denn an
Meinen
überhaupt?
kompletten Bildschirm? Na, der Benjamin eigentlich.
Okay, na dann
Hört
muss
ihr
ich
mich
mich.
jetzt?
Ja, jetzt hören wir
Ja.
dich, Anjuli.
Yay. Ich bin, glaube
Okay.
immer noch als du drin, Peter, aber warum auch immer. Oh,
Ja, das
Mann.
ist eigenartig. Aber benutzt du auch den Link, den du zugesendet bekommen hast?
Ja,
Das ist
Aber-
ja komisch.
ich habe sogar jetzt das Dashboard zugemacht, weil ich dachte, vielleicht merkt er, dass das Dashboard offen ist und ich da als du angemeldet bin. Ich habe die Cache geleert. Es ist einfach, naja.
Ah,
Nur nochmal
so
für mich. Jetzt seht ihr meinen Bildschirm nicht mehr. Jetzt seht ihr nur noch Peters Bildschirm, oder?
Nee, das ist Benjamins
Ja,
Bildschirm.
so
Es
mein.
Oder Benjamins
Es kann-
Bildschirm, ja. Weil du
es kann nur-
Benjamin zum Moderator gemacht hast.
Genau, nur derjenige kann seinen Bildschirm übertragen. Also es geht quasi nur einer. Also
Genau.
Okay.
Und man sieht quasi den kompletten Bildschirm, alles was drauf ist, außer das Overlay von GoToWebinar, oder?
das müssten wir jetzt quasi, genau, das sieht man nicht. Also wir können das ja mal testen. Es läuft übrigens auch schon die Aufzeichnung. Das ist ja jetzt nicht schlimm, aber ich weiß nicht warum. Ein bisschen
Ja, macht ja
eigenartig.
nichts, wir
Okay.
schneiden es ja weg.
Ja.
Liebe Grüße an meine
Also-
Mutti. Na.
Hallo, jetzt kann ich euch auch hören. Sehr schön.
Okay.
Muss ich wahrscheinlich noch mein Video hinkriegen, oder?
Genau, müsste noch. Also der anfängt, ist ja jetzt quasi Benjamin.
Wenke.
Müsstest du Wenke
Oder?
fängt
Hey, Wenke.
Ja,
Okay.
wartet mal, also ich muss mich noch hier alles.
Und es
Wir
gibt
schneiden
keine
ja das
schönen
alles
Hintergründe, oder?
Nee, gibt's hier
Nee,
nicht.
gibt's nicht.
Okay, gut. Na, dann sind wir halt heute alle zu Hause.
Okay.
Ah, das ist natürlich doof. Also schon so ein bisschen.
War auch gut.
Also
Ja. So, jetzt muss ich aber erstmal.
Also man muss
hier.
Wenke jetzt zum Moderator ernennen. Jetzt kann Benjamin nicht mehr teilen. Und jetzt müsstest du, Wenke, die Option haben, deinen Bildschirm zu teilen.
Warte mal, dieses Seitenteil hier, das ist alles so klein. Ich habe das gerade falsch geschoben. So, warte mal, jetzt habe ich hier Moderator ändern, übertragen. Ja, ich könnte was übertragen. Ich muss erst mal gucken, jetzt welchen Bildschirm ich wie übertrage. Oh, ach, das kommt jetzt hier drüben, sorry. So, da. Sie sind jetzt der Moderator. Schließen Sie die Fenster mit vertraulichem Inhalt. Jetzt ist mal die Frage, welchen dann. Wir probieren das jetzt mal, weil ich bin mir nicht sicher, welchen Bildschirm es überträgt. Ich habe ja 3.
Du kannst ja oben da ist noch so ein kleiner Reiter Übertragung, da kannst du dann auswählen, welchen Monitor du überträgst.
Mhm.
Da siehst du es vielleicht.
Nee, sehen tue ich es dort noch nie.
Sieht man deine Notes. Also PowerPoint.
Ich habe aber noch einen anderen Bildschirm. Jetzt muss ich erst mal gucken. Halt hier.
Aufnahme startet.
Welcome to the session Advanced Technologies and Hardware for Next Generation Computing, hosted by the Fraunhofer Institute for Photonic Microsystems, in short IPMS. The session today will be given by Fritz Herrmann, Benjamin Uhlich, and me. My name is Wenke Weinreich. I'm head of Center Nano Electronic Technologies, and it is a pleasure for us today to present our developments for next generation computing and MEMS, as well as the infrastructure capabilities of Fraunhofer IPMS on 200 millimeter MEMS and 300 millimeter CMOS technology. So this is the plan for roughly the next hour. At the beginning, I will give a short introduction to Fraunhofer IPMS. Afterwards, the Division Center Nano Electronic Technology presents its activities on neuromorphic computing for edge AI application and also its 300 millimeter screening fab. Then we will present our MEMS technologies and of course then the close with a Q&A session. So now let's start with the introduction to IPMS. The Institute Photonic Microsystems belongs in general to the Fraunhofer Society, and this is Europe's largest organization for applied research. With the goal of making our society competitive in the future for applied research, we work with industry as well as with public institutions. More than 26,000 people and 2.6 billions are deployed at more than 70 institutes to really transfer ideas to market from the first sketch to production. And of course, this is what also the IPMS stands for. The Fraunhofer Institute for Photonic Microsystems is a research and a development service provider in the field of microsystems and microelectronics. Our components and systems are used in medicine, everyday life, as well as in industrial environment. We are around 450 employees with a turnaround of roughly 45 million euros last year. And the Fraunhofer IPMS operates 2 clean rooms, the 200 millimeter MEMS clean room and the 300 millimeter CMOS clean room. At the Fraunhofer IPMS has 4 locations, and they are built up with really different competencies and partner networks. So we are double represented in Dresden with the 2 clean rooms. And then there's a facility in Cottbus called Institute for Integrated Silicon System. This was set up in 2018 with the main focus on monolithic integrated actuator and sensor systems and also on terahertz micromodules. And in Erfurt, optical solutions for biomedicine are being developed synergetically with 2 other Fraunhofer institutes. And können wir mal ganz kurz Stopp machen? Ich komme mit meinem Geklicke nicht hinterher. Also wir schneiden das raus und ich fange bei einer anderen Folie nochmal von weiter vorne an. Ich habe gerade gemerkt, dass ich hier das Foto vergessen habe. Bei den Folien noch nicht eingefügt. Soll ich das noch schnell ändern oder lassen wir das so?
Ich glaube, das kannst du so lassen. Dann sieht man Headquarters, ist auch gut.
Genau, das passt. Was ich nicht geachtet hatte, wie kommt das jetzt rüber? Ich würde zur Not nochmal von weiter vorne kurz anfangen. Hier sind noch viele Folienübergänge drin, weil ich das einfach nur reingenommen habe, die ich nicht brauche. Die stören mich gerade extrem. Die müsste ich noch mal rausnehmen. Sonst komme ich hier nicht klar.
Also
Kannst
mir
du
ist es
machen,
nicht
also man hat es
aufgefallen.
jetzt nicht gesehen.
Wartet mal, ich gucke mal noch. Gut, na dann lasse ich das so, wenn das okay ist. Dann fange ich mal. Wartet mal. Ist das. Dann würde ich hier nochmal anfangen, nochmal ansetzen.
Okay.
Genau. Da ist halt mal ein Schnitt drin, das ist sowieso egal. Man sieht ja, dass es dass es ja aufgenommen ist. The Fraunhofer IPMS has 4 locations. These locations are built up with different competencies and partner networks. So we are, for example, double represented in Dresden with the 2 clean rooms. In Cottbus, an Institute for Integrated Silicon Systems was set up in 2018 with the main focus on monolithic integrated actuators and sensor systems, and also terahertz micromodule applications. And in Erfurt, optical solutions for biomedicine are being developed synergetically with 2 other Fraunhofer institutes. Here we have a closer look on the locations in Dresden. So we have the 200 millimeter MEMS clean room and the 300 millimeter CMOS clean room, really in close vicinity to the large fabs of Infineon, of Bosch and Global Foundries. In Saxony, we can really look at the largest clean room accumulation in Europe with over 14 billion sales and 65,000 people. We form a unique semiconductor ecosystem in Silicon Saxony, and we are really one part of this ecosystem. Within Germany, a virtual factory of microelectronics was recently be set up, which bundles the competencies of 13 research facilities and thus allow tailor-made solutions to be provided for customers. And yes, for decades, we have been working successfully with corporations, medium-sized companies, and also startups worldwide. From USA to Japan, we are an established development partner for challenging products. And in doing so, we rely on a very stable network of partners, which you can see here. And Fraunhofer IPMS is also certified, and this, of course, ensures quality products and services, reliable pilot production, scheduling, and delivery. It also ensures that standards are maintained by annual assessments, and we also provide, of course, reporting and communication standards. That was, in short, the Fraunhofer IPMS. And now I will have a closer look at the activities on neuromorphic computing for edge AI applications, which mainly the Center Nanoelectronic Technologies has its focus on. The Center Nanoelectronic Technology itself is the 300mm division of Fraunhofer IPMS, running 4,000 square meter clean room with over 80 industry standard 300mm processing and lab tools. The CNT covers with this clean room several research focus topics in 2 business units called IoT components and systems and next generation computing. And these topics include, for example, the characterization, modeling, and design of CMOS integrated RF and AI components, low power functional devices like integrated capacitors, lithium-ion batteries, pyroelectric and piezoelectric sensors based on our long year experience in atomic layer deposition. Further topics are, for example, the CMOS process development down to the 22 nanometer node. We have activities in spintronics and emerging non-volatile memory, silicon photonics, and also quantum computing. But how can we contribute with our 300mm process platform to developments in artificial intelligence? And what is the connection to neuromorphic computing? To explain that, it is necessary to go one step back and look what AI stands for and how neuromorphic computing is connected to AI. In general, AI describes a program that can sense, decide, act, and adapt. So the main applications of such programs today are speech recognition and object recognition, and by various new mathematical concepts, and also some adaptations to the human brain, for example, by deep learning algorithms on neural networks. Artificial intelligence really already started to exceed humans in the performance for speech recognition or object recognition. Even by these systems, it starts that the applications are not only in the field of recognition, but the application starts to shift really to kind of generation. So it's really a high powerful technology. However, and that is the main issue where we are which we address, and what we are discussing is the power efficiency of such systems, even if they can perform like human brains, are really far away from any human brain efficiency. And that is the real challenge of today and of today's developments in artificial intelligence. So this leads me now really to explain a little bit what is the technological challenge of AI developments. And because all systems which are used for these calculations and to build the systems on rely on a classic von Neumann architecture in hardware. And this hardware or this architecture shown here means a really high load of data traffic through the so-called bus systems, even if you have really powerful CPUs, GPUs, or MPUs, which can really have a high performance. You always have a high data traffic to memories, which store the data. And by this high data traffic, you really, that means a high lack of latency and also a really high energy consumption. And one solution to resolve this problem is to go for new architectures of computers and to bring the computing unit in a very close proximity to the memory. And if we go even further for mobile or IoT devices, the processing, for example, is performed in the cloud, and you additionally need a very high data traffic between the cloud back and forth. And this again makes again a high contribution to latency, and you additionally need a lot of sending power. And here the solution for future edge AI applications would be a distributed energy efficient edge AI. And for that, you really know extreme low power hardware. And here you can see some of the applications in the field of edge AI that are, for example, of course, they have the image recognition for autonomous driving, voice recognition in the consumer or medical field, but also intelligent sensors in the industry. And all these applications need AI, but they need low power. They need decentralized, reliable processing. They need security. They need miniaturization and low cost. And so this is the field of edge AI. There's CNT sees its contribution by neuromorphic computing, mainly really implemented on neuromorphic hardware. Because I wanted to give also some notes now really to the word or to the field of neuromorphic computing itself. Neuromorphic computing is really one of the main solution for real energy efficient AI, but being able to address novel situations and to make abstractions like a human being. Neuromorphic computing combines the emulation of neurostructure of the human brain with probabilistic computing, which creates algorithms to deal with uncertainty, ambiguity, and also contradiction of the natural world. And the key challenge is really matching the human's flexibility and ability to learn from random signals with the energy efficiency of the human brain on chip level. And that is the crucial thing. And in this field, there have been several evolutions in the last year. So everybody speaks about 3 generations. Generation 1 can be equalized to machine learning algorithms, but already in the second generation, using deep neural networks, these networks go to the usage of the so-called in-memory computing and really new hardware architectures to realize finally a very high energy efficiency and parallelism. And that means high performance. So here, for example, non-volatile memories are used as weights in matrix multiplications. Thereby, for the whole systems, the race between analog, digital, or mixed signal concepts is not decided yet. So there's a lot of research going on in this field. The third generation not only uses neural networks with high parallelism, but in these so-called spiking neural networks, also the time-dependent activation and learning of human brain is tried to be implemented in hardware for an even higher energy efficiency. So here, the memories would be used as synapses and neurons. Here you can see that there are already a lot of developments worldwide with also a wide spread of performance and energy efficiency outcomes, but all of them are still far away from the human brain performance. So how can we as Fraunhofer IPMS contribute to this topic? So indeed, we develop neuromorphic hardware to implement second and third generation neural networks. We develop energy efficient microchips mimicking the human brain. They focus mainly on the development, the integration, architectures, and designs of low power non-volatile memories as basic device for all of these neural networks. So as basic device, for example, as weight, as synapse, or as neuron. And we see the so-called ferroelectric field effect transistor based on ferroelectric hafnium oxide as the most promising candidate for future processors. Why do we do that? Ferroelectric hafnium oxide was discovered in Dresden many years ago, and the developments on FIFET we could really accompany from the beginning on. Now, hafnium oxide is a really intensively studied material worldwide, and we use this material, or we study this material for the application as so-called FIFETs, ferroelectric field effect transistors. These FIFETs are ultra low power, low latency, cost-effective, non-volatile memory bit cells. There exists already the implementation for the 28 nanometer high-K metal gate and 22 nanometer FDSOI technology of global foundries. The advantages of this memory are a really very high memory window, a very high on-I-off ratio. You have really low write power unit, and you also already have a very good device-to-device variation and good data retention. But yes, the really great benefit is the option of a dual integration really together with the logic of CMOS, which yes, in all technologies starting from 28 is always with a high-K metal gate from the same material. So we start now to really implement these FIFETs for both generations 2 and 3. And for example, or you can see here the example where we try to implement the FIFETs in analog computing memory accelerators. For that, for example, we had to develop a new bit cell configuration, which a really low device-to-device variation. But we also started to develop the periphery you need for such an accelerator. So we developed, for example, together with partners, a low-bit ADC concept with a superior area and power efficiency for current sensing. We could show that there's no accuracy drop in digitalization if we include these FIFETs in such a system. We could already reach really high power efficiencies, and it was shown that there's really also no accuracy drop if we tried this accelerator with different neural networks and if you really try to run it in an application. And here you can see that we really already did a great step forward with our developments to the direction of human brain performance and efficiency with our developments. And We also started to characterize and optimize the FIFET for applications in spiking neural networks. So first studies show that FIFETs have the necessary properties of analog switching and high linearity that are needed to be a neuron or which are needed to learn like a synapse by spike time dependent plasticity. So here we are really going forward in studying the devices to bring it also to this application. And finally, yes, how to perform these studies and to finally build such complete systems out of this new device. Yes, we use for that our IPMS FIFET short loop and research platform. And this covers, for example, our own test chips, electrical characterization with high statistics, and also fundamental material characterization. To implement products later on, we rely on the 22 nanometer and 28 nanometer technologies of global foundries. And overall, we work together with a lot of partners in Europe and worldwide to reach the aim of a really high performance and low power edge AI microprocessor based on FIFETs. So that is our aim and our goal in our developments. And now I would hand over to Benjamin Ulich, who will show you, yes, in more detail, who will explain in more detail the 300 millimeter process platform of Center Nano Electronic Technologies. Thank you.
Okay, so hello everyone, and welcome from my side to our hosted session from Fraunhofer IPMS. My name is Benjamin Ulich. I'm leading the business unit Next Generation Computing here at IPMS. And today I want to present you our Fraunhofer 300 millimeter screening fab. So I will talk a little bit, what is this screening fab, how does it look like, and what is the concept behind it. And I want to also show some examples from some technologies and equipment we can offer you.
Sorry, Benjamin, ich muss dich kurz unterbrechen. Ja. Bei dir sieht man auf dem Bildschirm noch den Bang & Olufsen Einblender mit dem Mikro. Okay. Den müsstest du nochmal ausmachen, dann musst du nochmal anfangen. Sorry.
Ja. Jetzt habe ich ein bisschen meinen Flow.
Jetzt hängt er so links oben, stört er nicht so sehr.
Achso, warte mal, das ist aber auch blöd. Geh mal weg. Geh weg. Nee. Was macht denn der hier? Wozu gehört denn der eigentlich?
Der gehört zum Laptop-Mikro.
So. Dann gucke ich mal. Hier. Verlassen. Nee. Jetzt ist er weg.
Jetzt ist er weg. Ja. Mhm. Okay.
Okay. Dann fange ich mal neu an. So, okay. Sieht man wieder den Startbildschirm?
Ja, alles gut jetzt.
Good. Okay, hello everyone and welcome to our hosted session from Fraunhofer IPMS. My name is Benjamin Ulich. I'm leading the business unit Next Generation Computing at Fraunhofer IPMS, and today I want to present you our Fraunhofer 300 millimeter screening platform. So I will talk about this platform, what is it, what is the concept behind it, and show you some examples of available technologies and equipment. So you've already seen this picture. It all revolves around our clean room, 300 millimeter fully CMOS standard clean room with 4,000 square meter space and more than 80 300 millimeter tools, which is located in the Dresden vicinity. How does our clean room look like? So I want to show you a small layout of our 4,000 square meters. We have different modules here in this clean room. So we have all the equipment for wet processing. That means plating, CMP, wet etch. We have a litho cluster centered around our 300 millimeter E-beam direct writing. We have a few tools regarding plasma etch. A lot of tools regarding various deposition techniques like ALD, CVD, or PVD. And of course, we need metrology to characterize our process and have qualified results. What is the concept behind the screening fab? So with the screening fab platform, we want to bridge the well-known gap between fundamental research and manufacturing. So what we want to do and what we have done is take up very good ideas from fundamental science, from the lab scale, and put it into the manufacturability and put it into the fab scale, basically. We do this with many partners from the semiconductor industry. For example, for material suppliers, we offer our capabilities that they can really qualify or enhance the values of their product. For example, if they want to implement a new cleaning chemistry to their customer, they can come to our facilities, test their new products on really industry-grade equipment, and get meaningful wafer level data to present these data to their customers. And on the other hand, we also work with the IDMs and foundries. So for example, the foundry can test or optimize their processes. They can look and screen for new chemicals at our site. So they don't have to pull out their tools from production. They can save basically time and money and do this at our site, and they can send their wafers to us. And a third possibility is, of course, for equipment supplier, where we offer our infrastructure. We have all the needed pre and post processes and the metrology you need for this. So with this screening fab, we cover a wide range of material process integration solutions, from consumable benchmarking over more research like new technology development, but also reducing costs or increasing the yield of the products. Special mention maybe to our wafer loop concept. With our state-of-the-art 300 millimeter clean room, we have established several protocols regarding contamination and quality. And in the past, we have shown with one of our biggest foundry partners, Global Foundries, that we really match their processes. So we could show that we basically get the same electrical data when the wafers run through our fab, for example, in the back-end of line module, compared to when the wafers run through Fab 1 in Dresden. And with this, we are able to really loop product wafers with major companies like Infineon and Global Foundries. I now want to present some examples, so some selected process and equipment from our screening fab portfolio. First, a slide for plasma etch. We have 3 main clusters for dry etch, 2 from Applied Materials for front end of line and back end of line applications, and 1 new cluster from TEL with a brand new Vigus LK3 chamber. And with this chamber, we can target back end of line dielectric etch applications down to the 40 nanometer node. It is equipped with RF pulsing and can also do atomic layer etching. On the clean side, we are happy to have acquired a new cleaning tool from Screen through the FMD, the Forschungsfabrik Mikroelektronik Deutschland. This is a single wafer cleaner with 2 chambers for front end of line and back end of line wet etch applications, and an additional chamber for bevel and backside clean. It is configured very flexibly. We have a lot of different chemicals, ultra diluted HF, all the acids you need, and also several containers for custom applied chemicals. On the CMP side, we rely on our armored reflection LK CMP system. Originally, it was used for the normal back end of line copper and barrier polish processes, but we recently upgraded the endpoint detection system to also cover oxide and STI polish processes. On the ALD and CVD side, we have a long history of different process applications. We have a lot of capabilities to deposit really high K oxides, so we can deposit hafnia and zirconia also in high aspect ratio applications. We have a new emerald chamber for PE ALD silicon oxide liners, some batch ovens for titanium nitride or silicon based materials like silicon germanium, also epitaxially. And we acquired 2 new PE CVD platforms for oxides, nitrides, and low K and ultra low K materials. On the PVD side, we have 2 Endura clusters from Applied Material. One is for metallization applications for standard copper and barrier tantalum-based materials, also with a cobalt MOCVD chamber and an in situ XPS analytic chamber. And recently, we acquired a new Endura platform with several Clover-based chambers, which can support up to 5 different PVD targets. And with this platform, we are able to really target state-of-the-art research for advanced spintronic devices like MRAM, for example. For all these processes, of course, you need the appropriate metrology and analytics. So we have the inline clean room metrology you need, like thin film measurement, defect measurement, and resistivity measurements, and so on. But we also have a few analytic labs for really advanced nano analytics. And some special mention there maybe to our new SEM supplied with an EBSD detector and a new TKD detector for really compositional analysis, an AFM with a possibility to do piezo force mode for our ferroelectric applications, and a new XPS system with a double chromatic source. Last but not least, we have a huge variety of electrical characterization and test, from really coupon level to automatic wafer probers with 200 and 300 millimeter wafer uptake. The main applications here are non-volatile memory characterization, but also interconnect and reliability tests. And in the near future, we will upgrade even to magnetic material and device tests and cryogenic probing. You can find all these additional information in our process catalog at our virtual booth additionally. So maybe at the end, some success stories of our screening fab from previous project. During the last years, we established a multi-year cooperation with one of the largest chemical suppliers for copper electroplating chemicals. So we really enhance their products in that they send us their chemicals and we provide them with 300 millimeter wafer level data so that they can further improve their products. We have a strong partnership with semiconductor manufacturing foundries and IDMs. And for example, in the CMP consumable benchmarking field, we did a very large benchmark project for CMP consumables, and in the end, the basically winner of this project really became the POR of this foundry. But not only for big foundries, but also for smaller companies. We work together with a regional foundry, with a regional company who develop phase fluids, which physically remove layers. And we enable them through several projects to really get food into the microelectronic industry. So with this, I want to present you again the advantages of our screening fab. So really with us, you can get wafer level data and benchmark your product through our state-of-the-art CMOS clean room with the appropriate metrology and analytics. We have really fast development cycles and then the high tool availability. And with our established contamination and quality protocols, we are even able to loop real production wafers with our partners. There's strict IP management, no data gets out to third parties. And with our scientific knowledge and engineering knowledge in our network, we would be happy to really work together with you. You can find more information at screeningfab.com. And with this, thank you for your attention and looking forward to any questions.
So hello also from my side. My name is Fritz Hermann. I'm the technical sales manager of Fraunhofer IPMS 200 millimeter line. And I want to get into detail what we do there and what is the MEMS Technologies Dresden. So our vision is that we get customized solutions for our customers, that they get what they are looking for, and we have what we can offer in this field is the very experienced part for technology transfers in and out of a clean room, especially our clean room. And we are experts in technologies and processes that running in our clean room and those kind of clean rooms. And what is very interesting probably for customers is that we are working very close to industrial fabs, and we have those kind of standards on the one hand side by the management of the production, but also with the tools and the processes that we use there. What are we focusing on with our devices? So we do produce devices that getting used into a lot of fields of application. These are the three main application fields that we targeting. One is the industrial solutions field. The other one is the quality of life, and the third is medical health. So these are the big trends today where MEMS devices are getting used. I'm going more into detail on the next slides where these devices find their place. But first of all, let's have a look on what kind of devices do we researching on, and what kind of devices are getting into the industry from our Fraunhofer IPMS, especially the 200 millimeter line. Our spatial light modulators are very famous all over the world. They are highly precise, and yeah, this is a technology which is very critical, and we are happy that we managed to have experience over now 10 years in this field. Also, what we do there is, for example, the capacitive micro machine ultrasonic transducers. These small devices are very interesting when we think about imaging, sensing, or movement detection. So yeah, on the one hand side, we can find those devices in consumer electronics, but also in the field of medical health. What we also do is building up MEMS scanning mirrors up to sizes to 1 to 5 millimeters. These devices are getting used nowadays for LiDAR applications, and in the past it was used for laser scanning applications and so on. Last but not least, on this slide, I highlight the end-of-line substrates, standard substrates, where we also put a foot into the organic electronics, where our substrates, which are standardized and now developed over 10 years, are used to characterize organic materials, for example, in the solar industry. How do those devices get designed, and how do those devices get manufactured in our MEMS Technologies Dresden fab? So the one technology approach that we use is the surface micromachining. It's a common approach for the development of MEMS devices. typically you use a bare silicon wafer, build on top a sacrificial layer, then you get your movable parts on top, and at the end of the process you release the sacrificial layer so that you get the movable part and the device can run. For example, CMATs use those technologies, or in-house we use them for the spatial light modulators. The other big technology approach is the bulk micromachining. There we use the capabilities of reactive ion etching, where we get deep structures into the silicon wafer, so into the bulk. And with this approach, you reach aspect ratios up to 40 and you get movable parts, as you see in the SEM picture. For example, we use this approach for the scanning mirrors or the nano E-drive technology, which I will highlight soon. What's also interesting, but kind of a niche in our portfolio, is the active silicon, where we use active materials to sensor the environment, to get sensing of the environment. In this particular, we use them to measure pH values, and it's used in production environments and so on. What becomes more and more important to the MEMS manufacturers, also for us, is the integration for MEMS on CMOS. That means you get a CMOS by a foundry, for example, X-FAB, and we build on top the interconnection, and then since the interconnection is done, we can build on top the MEMS device to shorten the time to market for our customers, and also to increase the density on the wafer to get more devices done. How do these approaches fit into the fields of application? As I said, we have lots of devices used, but these devices are getting used into a big field. For example, when we have a look on the CMATs, we have the CMATs used in mobile devices, but also CMATs are used for medical devices. Here you can see a picture where a CMAT is used to detect whether an ear infection is viral or bacterial, and so the person who is covering can get antibiotics, whether it's bacterial or infectious. You see here in the middle the microspeakers, which are right now becoming more and more popular, because these are the first microspeakers done on MEMS devices or with MEMS devices, which has several advantages. And we are leading this technology, and this is the technology which is called nano E-drive, which becomes more and more into focus, and which is also used in a big variety of applications, not only the microspeakers. Right down below, you see the micro pumps and the micro valves. These are also pumps and valves based on this specific technology invented by Fraunhofer IPMS. On the right-hand side, you see the thermopile arrays, which we are developing and manufacturing with our partner Heimann Sensor and X-FAB together. And this becomes popular more and more, because since we had COVID last year, these thermopile arrays are very important to detect the temperature of bodies. So you can get an idea, for example, on the airport, whether a person is sick or not. And so since the temperature of the body increases, those thermopile arrays can detect it, and this leads into a high demand of these devices. Now I want to give you a brief overview about the NED actuator technology, because this is what we want to show you in particular, because this technology was, as I said, first ideated in Fraunhofer IPMS, and now it becomes into a fabrication level where we can produce for Arioso systems micro speakers, or the MEMS device for the micro speaker, and to show you where it's also possible to use, you see here a brief overview. For example, you can use it for all silicon.
Sorry, dass ich nochmal reingrätsche. Fritz, du bist bei mir stumm. Geht's den anderen auch so?
Ja.
Aber er hört uns nicht, so wie es aussieht.
Mist. Fritz? Nee.
Ja, dann kill mal seine Präsentation.
Jetzt merkt er es, aber er kann es ja trotzdem nicht hören. Warte. Tja. Ja, Peter, ich weiß auch nicht, ist dir das schon mal passiert? Soll er sich nochmal aus und wieder einloggen?
Oh, nee, ich würde sagen, irgendein Bluetooth-Gerät hat sich bei ihm verbunden. Und ich versuche mal.
Warte mal, wenn ich es im Chat schreibe, vielleicht sieht er es dann.
Ja, ansonsten, ich mache mal mich zum. Geht das? Ich kann nicht meinen Monitor übertragen. Sonst übertragen wir deinen Monitor mit irgendwie mit einem Word-Dokument. Ich kann das irgendwie bei mir jetzt gerade nicht machen. Warum auch immer.
Warte mal, ich gebe es an dich weiter.
So, sieht man meinen Bildschirm?
Ja.
Sieht man die PowerPoint?
Momentan sehen wir einen blauen Hintergrund. Gerade eben war es da.
Jetzt höre ich euch wieder.
Ah, okay,
Ja,
sorry.
sehr schön. Okay.
Eieieiei.
Okay. Also dann gebe ich dir das Recht wieder.
Muss die Frage noch gelöscht werden? Nicht, dass die jetzt im All-Chat sozusagen auftaucht, oder ist sie nur intern von uns?
Die ist nur während der Session jetzt, ne?
Die sieht man nicht auf dem Video.
Alles klar. Seht ihr meinen Bildschirm?
Jetzt sehen wir es wieder. Also bei der Folie müsstest du jetzt nochmal einsteigen.
Okay. Na dann. Here we can see how the nano eDrive actuator technology is also used beside the pumps, the valves, and the micro speaker. Here you see that it's also getting used for ultrasonic transducers or positioning platforms. So this technology has a huge impact on a lot of applications, and we are happy to have the time to present in this conference what is also possible. And to get more into detail to that, we have Bert Kaiser, which is the head of the group which develops those devices, and he will have a presentation or a talk with the title All Silicon Ultrasonic Recognition of the Environment, which focus on the nano eDrive technology and its huge advantages. So feel free to join in there. But what I want to focus on is how to get those devices are manufactured and what capabilities are necessary. We use, as I said, the deep silicon edge to realize those structures, those 3D structures into the bulk, the silicon. Also, we use PVD to get all these reflectivities on the devices. Those technologies mainly use BSOI wafer as base materials and grinder to thin them down later in the process. And on this part, we recognized in the past that BSOI wafers are have a highly demand in the market, and we had long time to purchase those kind of wafers, and this was the point where we figured out whether it's possible to get those wafers on our own for our own devices, and we did those wafers on our own. And now what comes to our mind is that we could use those self-made BSOI wafers and customize them with things that we are strong in. That means that we get those wafers with features such as cavities or buried metallization. And so this is what we focus on when we do BSOI wafer on our own to get the requirements for high sophisticated devices achieved. Therefore, we have had the chance to get a grinding tool via the FMD, which was also already mentioned by Benjamin Ulich recently. The FMD is a society which brings all the Fraunhofer institutes together, which are working in the field of silicon. And so we had the chance to get a grinding tool, as I said, for the wafer thinning and also for the BSOI preparation, which we have done so far externally, but now we can do it on our own. And which is very unique is that this grinding tool is CMOS compatible. So when we take a step back and have a look what Fraunhofer MEMS Technologies Dresden is offering, is that we can go from a very basic idea and can do a research and feasibility study based on MOEMs and MEMS devices. And then we bring those ideas into a design, we develop a process, get done demonstrators and prototypes for devices on wafer level, and later on we have the capabilities as well to get these devices into a pilot fabrication. Later on, which is not often the case, but we have the opportunity to hand over our knowledge on pilot fabrication to high volume fabs if it's necessary for special devices. But overall, all devices that have been developed on our side had been fabricated by Fraunhofer IPMS. Where do we do this? On the one hand side, the 300 millimeter standard nanoelectronic technologies clean room, which Benjamin and Wenke already highlighted, and we as the 200 millimeter line focus on the MEMS devices with our facility. What is this facility about? Some hard facts. We do, as I said, the research and development, but also the pilot fabrication, and this is a bit contrary to each other, but we managed to get those two opposites together, and we call this the low volume high mix approach, and it works very good, especially for our customers, because we have knowledge of over a lot of devices and processes. We run in a 24/5 shift operations. This means that we are close to industrial fabs, and our clean room is never standing still. It's running all over the week. Nowadays, we use a 365 nanometers I-line lithography tool. I will go more into detail on the next slide. Our newest highlight, the DUV cluster. But what is important for us is that we have a lot of wafer starts per month, around about 1,000 wafer per month, which is a very high number for R&D clean room, which also shows that we can, that we do pilot fabrication. We are CMOS compatible, as I said, and we are ISO 9001 certificated. Here is our newest tool, which is the DUV scanner. We have a dedicated coder and a track for this DUV scanner, and there we get new resolution levels done, which means that we can achieve 130 nanometers lines and spaces with this tool. And also we had the chance also with the FMD to get the measurement tools within this purchase, which means that we have a new overlay tool, and our CDSM tool is possible to work with this tool together. Maybe you have seen this already on our Fraunhofer IPMS LinkedIn profile. There is a interesting video about how we got this tool into the clean room over Christmas. This video shows the big challenges of getting such a tool into a clean room, and if you like, I only can invite you to visit our page and watch the movie. And maybe if you want, you can also follow us on LinkedIn since you're there. Thank you for your attention, and if you have questions to Wenke, Benjamin, or me, don't hesitate to ask. Thank you.
Okay, super. Wir sind ja fast durch. Fritz, würdest du nochmal aufhören zu teilen? Dann machen wir nochmal Wenke und Benjamin ihr Bild an.
Oder wie kann ich ihn aufhören zu teilen? Hier.
Genau. Und dann haben wir so ein Ende-Standbild und da würden wir dann einfach noch dahinter ein Bild tun zu jetzt geht's los mit der Q&A-Session. So, ich halte jetzt mal die Klappe ganz kurz. Ihr lächelt freundlich. Hervorragend, das reicht ja schon. Okay, gut. Dann stoppe ich jetzt die Aufzeichnung. Peter, ich drücke einfach Aufzeichnung anhalten, oder? Dann speichert automatisch.
Ja, das reicht.
Okay.